Hello everybody. In Learning Module 6, I initially had plans to go over the regression example that I discussed on October 27th. But since that part has already been done, I want to build on that and do a couple of things. First, I want to show you how this is done in R. Now, I have partially shown how ANOVA is done in R. I have not shown you how a regression is done in R. For both of those, a common factor is the fact that a certain column, if it is having numerical data, let's say in 1, 2, and 3, even if those are levels, that part needs to be trained for R that it is a level as opposed to numerical data. So we have to make a little adjustment to the data set. But beyond that, everything else, if the data is already character, like male, female, then by default, R will already capture that as a factor. And then eventually, once you run the model, the rest of the process becomes very simple. So what we'll do is the two data sets that are part of your assignment 6A and 6B, we will look into how to run those models in R. And as you will see, because R is a statistical software, you don't have as much of coding to do. A lot of that is done internally by R. And once we are done with that, we will look into another data set that we had visited at the beginning of the semester on bank salaries. If you recall, these were salaries of individuals with different levels of competence, previous work experience in the banking sector, outside the banking sector, um, education level, and so on and so forth. And so we will apply our 7-step method to that data set and do that entire exercise again, both in Excel as well as using R. So without further ado, let us look at our data set for assignment 6A. This is the same data set that you and I discussed on the week of October 27th. So this is the pricing data set, right? So these are a list of homes coming from different neighborhoods with a certain set of offers, square footage, whether it's a brick house or not, bedrooms, bathrooms, price. So real quick here, we know price is the outcome or the response variable y, right? And it's in dollars. So it's a numeric data. Bathrooms, bedrooms, they're all numeric data as well. Square footage and offers are also numeric data. Now, if you look at the column brick, because it is defined as a category of no versus yes, when it comes to R, we don't have to do anything else. R by default picks it up as data with factors, as a factor data with two levels, no and yes. And then the only one that we have to train R is the neighborhood column, because that's the only one that when R picks it up, it picks it up as a numerical data, and we just have to let R know that the numbers there are actually levels of a factor, and to treat the neighborhood as a factor. Okay, so once we do that, the outcome would be very similar to what you would see in your Excel. So let's look at it from the context of R. In R Commander, what we'll do is we will go under data, we will import data from Excel file. In this case, let's call this home prices. Okay, and I'm going to make the data set's name such that there is no gap in between. It's a continuous single word. And see, as you can see, variable names in first row of spreadsheet. So by default, it is the way it is defined. So the first row always gives the label, as they say in Excel. Row names in first column of spreadsheet. Um, Not necessarily so. I saw that part has not been checked. Convert character data to factors. So because that part is checked, when you look at the brick column, which is a yes versus no, by default, it will convert that into a factor with two levels, yes and no. So I hit OK, and it asks me which dataset I'm looking for. I'll choose the week 2 dataset 1, um, and within that, I'll just choose the data tab. Okay, so um, it then tells me the dataset has 128 rows and 8 columns. Okay, so right now you can say that your data set is home prices, which has all of those rows and columns. So as I said before, my only training that I need to do with this data set is simple. I need to just convert the neighborhood into a factor. So I go under data, I go under manage variables in active data set. In this case, my active data set is home prices. So under data, manage variables in active data set, I scroll down to convert numeric variables to factors. Okay, and I choose the neighborhood variable. Instead of trying to supply level names, I'm going to use the same numbers that I have, 1, 2, and 3. Only this time, they're going to be treated as factors. And it says new variable name or prefix for multiple variables. Let's keep it the same name as the variables, which is neighborhood. Okay. By default, it will choose multiple variables, as you will see in the outcome analysis, but we'll keep it as neighborhood. Let's hit OK. It says variable neighborhood already exists. Override variable, yes. And so now the neighborhood variable has been loaded as a factor. Now we are ready to run our regression. So this is what I do. I go under statistics, go under fit models, choose linear model. Okay. And I can name the linear model as prices regression. Okay. So the linear model is set up in such a way that you have only one y variable and the rest will be x variables. Okay, and every time you choose the variables from this list, you double click that variable. The first one that you double click will be by default your y variable. So of course your price is what you are choosing as your y variable. And you are essentially trying to define price as a function of all of the other variables. So this is where bathrooms, bedrooms, brick. I won't choose home because if you recall, the first column was home. It just basically tells you the home number. Neighborhood, offers, square foot. So these are the 6 variables around which I'm trying to define price. I hit OK, and it gives me an outcome of all of those coefficients. Now, if you compare this with the outcome that we have seen in Excel, it is exactly similar. Okay, and by default, as you can see, it is doing what the dummy variables does for you. So it has 3 levels of neighborhood. Okay, so it has chosen neighborhood 1 as the reference and used it for neighborhood 2, neighborhood 3, and it has given you the corresponding estimates that will allow you to compare the price against the reference of neighborhood 1. In the same way, for brick, it has chosen the yes option, and based off of that, it has given you a price so that you can now compare with the non-brick or the no option based off of this estimate. So first things first, when you are asking yourself, how do I compare this output with what I see in Excel? It is rather simple. So the first part of Excel, if you recall, in Excel, you have three parts to the Excel output. The first part talks about explainability. So that is given in your explainability part here, right? The 0.8686 or 0.861 adjusted R square that basically tells you that 86% of the variability in Y, in this case the price, is explained by the combined impact of all of these variables taken together, which tells you that it's a good model. It's a very healthy model to work with. That same story is told by the second part of the Excel output for regression, which is your ANOVA table. This is where you get your F statistic and the corresponding p-value. And as you can see, that p-value is less than 2.2 times e raised to negative 16, which basically means the p-value is less than 2.2 times 10 raised to negative 16. Or you can start 0.000000 up to 16 zeros, and then comes your 2.2 or 2.2. So it's a very, very small number. And of course, your p-value is less than alpha. And so you wholeheartedly say that your model exists. It's a valid model to work with, which is when you start looking into these estimates. And so, as you could see in the very similar way that you saw in your Excel output, except for the intercept and the neighborhood 2, everything else are statistically significant to stay in the model. And therefore square footage stays in the model. And the way you look at it is you look at this p-value, it is extremely small, again e raised to negative 15. And so that estimate or the coefficient of square foot is actually a valid one. It allows you to keep square footage in your model, and your interpretation is that for every square footage your price increases by $52. Offers, and we talked about this again, statistically it's significant to keep in the model because of that very low value. It essentially means that for every extra offer your price is reducing by $8,267, right? So you ask yourself, what could this be attributed to dynamically? And a possible scenario may be that it is not a seller's market, and therefore the more the number of offers are coming in, you are forced to reduce the price, which is probably causing that attribute. Let's go with the easy ones. Bedrooms, again, 0.00894. So yes, very, very significant. And we are counting significance for 0.05. Here, as you can see, it is giving you all possible significance codes. If you want to count a 0.1% significance or a 1% significance or a 5% significance and so on and so forth. Okay, we are only looking into 0.05 as my alpha. Okay, so 5%, anything less than 5% means that that specific variable stays in the model. So for every extra bedroom, the home price increases by $4,246. For every extra bathroom, the home price increases by $7,883. And this is an interesting point to note that home buyers typically value the bathroom more than the bedroom. That's something to really ponder about. Now, brick. Again, statistically, it is significant to stay in the model. That 17,297 basically tells you that a brick house is $17,297 costlier than a non-brick house. Again, the reference point is what is not used here in the model. So the non-brick house is the one that was no or a 0. In the same way, when you look at neighborhood 3, again, it's statistically significant. And therefore, you can see that homes in neighborhood 3 cost $20,000 more than homes in neighborhood 1, because neighborhood 1 is your reference. In the same way, you may be inclined to think that homes in neighborhood 2 are $1,500 cheaper than homes in neighborhood 1, and that would have been a valid statement. However, if you look at the corresponding p-value, it's a very high p-value. It's much higher than 0.05, which basically tells you that it's not statistically significant. In other words, you can't keep this one in your final model equation when you write your equation. And for layman's terms, it basically tells you that statistically there is no difference between the prices of homes in neighborhoods 2 and neighborhood 1. Whatever difference happened just by chance because of this sample. But statistically, there is no difference. And that's what you're concluding. So that, in my 2 cents, is how you can use R to run the regression. So the regression process comes once again from going into statistics, going into fit models, going to linear model, and start building that regression model. Okay, so make sure that you choose the right factors that build the regression. And therefore, it is important that you define specific columns that need to be taken as factors, or else you wouldn't get this kind of outcome that you are seeking. Hopefully that helps.